Hello friends, this is lecture 2 of numerical analysis. In this lecture, I provide some important notes about iteration methods. So the first part is given in iTab. If you don't watch my first part video, then refer to iTab. So let us start this video. Now, general iteration methods. So the iteration method considered in the previous section are special case of the following iteration method, that is xk plus 1 equal to phi of xk. So in this previous iteration method we have already discussed about bisection method, regular Fulci method, Newton-Raphson method, etc. So here this is the general iteration method, and this xk plus 1 this gives phi of xk, and the function this phi of x is known as the iteration function. So let us first discuss what is first order method. So the sufficient condition on phi of x for convergency is given by, so if we write fx, our given a function is fx, and from this we get another function phi of x, and this phi of x is converges, then a theorem is given by. So here the theorem says that if phi of x is a continuous function in some interval of closed interval of ab, that contains the root, this closed interval contains the roots of the this phi of x, then and this phi dash of x, this mod is less than equal to some constant c, which one is less than 1 in this interval, then for any choice of x naught belongs to the closed interval ab, the sequence xk determines from this xk plus 1 this equal to phi of xk, where k equal to 0, 1, 2, 3 converges to the root this xi of x equal to phi x. Clear? So here we assume the root is xi, and this xi is lies in the interval this ab, and we choose for any x naught belongs to the closed interval ab, the sequence this xk determined from this phi of xk plus 1 equal to phi of xk, which one is the converges. So here the constant c is called the Lipschitz constant. Clear? So this is a theorem. Now come to definition, that is the interpolation theory. So how this interpolation work, and how we find the interpolation function px, and what is the actual function. We have a function fx, and there are certain nodal points, and from by using these nodal points we approximate a polynomial px, which one is called the interpolation polynomial, or this complete theory is known as the interpolation theory. So in the definition says that a polynomial px is called an interpolating polynomial if the values of px and its certain order derivative coincide with those of fx and its same order derivative at one or more tabular points. That means we have a function fx, and there are some tabular points of fx, that is x0, x1, x2, x3. In this point we get f of x1, f of x2, f of x3, etc. So at these nodal points our the interpolating polynomial px also gives the same values of fx. This condition is known as the interpolation. Clear? Now before going to interpolation theory, there is an important polynomial. This is called the Taylor series polynomial. So this says that if the polynomial px is written as Taylor expansion for the function fx, given a function fx, and we approximate this fx in terms of px, and this approximation by using Taylor series about a point this x0, and this x0 is always belongs to closed interval ab, in the form of how this px is written as. So the Taylor series is given as f of x naught plus x minus x naught into f dash of x naught plus x minus x naught square divided by 2 factorial into f double dash of x naught, and this goes on up to x minus x naught to the power n divided by n factorial into f h nth derivative at x naught. Clear? Here also we get the error term. So this I can explain in another slide. So then here the px may be regarded as the interpolating polynomial of degree n satisfying the condition ph kth time derivative at x naught is always equal to fh kth time derivative at x naught, and here this k value lies from 0 to n. Clear? So that means this polynomial px and the polynomial fx, which one is our original function, and we approximate as px, and these derivative of this function and the polynomial are same at these nodal points. That means at about this point x naught. Clear? Now come to the remainder or the truncation error. That means what is the error of this polynomial. So here the function fx is given and we approximate this as the px, and this px we approximate this by using the Taylor theorem. So what is the remainder or what is the truncation error? So the remainder term is written as the Rn, and this Rn gives the value 1 by n plus 1 factorial into x minus x naught whole to the power n plus 1 into fh n plus 1th derivative at the point xi, and this xi value lies between x naught to x. Clear? Here the truncation error bound is 1 by n plus 1 factorial into x minus x naught to the power this mod to the power n plus 1, and this m n plus 1 less than equal to epsilon. Clear? And this mn plus 1 is maximum of a less than equal to x and less than equal to b. That means in this interval ab we choose the value of x, and the maximum value uh, that is calculated by using f as the n plus 1th derivative at x. So first of all we have to differentiate the function fx with n plus 1th time and take the mod and find the value of the putting this value of x here and find the maximum value which gives our m plus 1. So for this total thing, let us take an example so that we can clarify this clearly. So here a question is given. The question says that obtain the polynomial approximation px to fx equal to e to the power minus x by using Taylor expansion about x naught equal to 0. Our x naught point is 0 and our fx is e to the power minus x. We have to find the px by using Taylor expansion, and we have to determine first bit says that x when px obtained from the first four terms only each to be less than 10 to the power minus 6 after rounding. Here given with after rounding. Clear? And second bit says that the number of terms in the approximation, that means how many terms are required for this approximation to find the result correct up to 10 to the power minus 10 for the x value lies between 0 to 1. Clear? So here a value is 0 and b value is 1 and x value lies between 0 to 1. Clear? So first of all let us solve first bit, and first bit says that here fx equal to e to the power minus x and f dash x is equal to minus 1 into e to the power minus x, because derivative of e to the power x equal to minus e to the power minus x. Similarly, if we find the rth time derivative, then this gives minus 1 to the power r and e to the power minus x, and this we run this r value from 0 to 1, 2, 3 and so on. Clear? So Taylor expansion is given as this px equal to f of x naught plus x minus x naught into f dash of x naught plus x minus x naught square by 2 factorial into f double dash of x naught and so on. Clear? So we have to find the first four terms only. So first four term is f of x naught. So f of x naught, here x naught value is 0. So f of x naught equal to e to the power 0. E to the power 0 is 1. Clear? And here also x naught equal to 0. So this one is x into f dash. So f dash is this one is 1. That means this one is 1 minus x plus x square by 2 minus x cube by 6. That is 4 term. 1, 2, 3 and 4 term. Clear? Now once again first 4 term only is to be less than 10 to the power 6 after rounding. That means we have to find 10 to the power minus 6 after rounding. So now error bound is given as 1 by n plus 1 factorial into x minus x naught to the power n plus 1 and m n plus 1 less than equal to epsilon. This gives the error bound in Taylor series expansion. So here x naught value is 0 and we have to put what the n value and we have to find the epsilon. Clear? So let us find out. Here x naught equal to 0 and take n equal to 3, then we get 1 by 3 plus 1 factorial into x minus x naught to the power 3 plus 1 and m4 is less than 5 into 10 to the power minus 7. So here 5 into 10 to the power minus 7 here given as though we have the rounding of the value. So rounding value is 10 to the power minus 6. So we have to take the next digit, that means 10 to the power minus 6, then 10 to the power minus 7. If we write 10 to the power minus 10, then 10 to the power minus 11. So similarly for rounding we get 5 into 10 to the power minus 7. Clear? So here 1 by 3 plus 1 factorial is 1 by 24 into x to the power 4 into m4 is less than 5 into 10 to the power minus 7. So here we have x to the power 4 into m4 is less than 24 into 5 into 10 to the power minus 7. Clear? So here 24 into 5, this gives also we have 120 into 10 to the power minus 7, and we have to find what is m4. And m4 is maximum of 0 x value lies between 0 to 1 and f has the fourth derivative at x. So here maximum of this f has fourth derivative is equal to e to the power minus x, and on mod we get this value is 1. Clear? M4 equal to 1. So putting m4 equal to 1, we get x to the power 4 into 1 is less than 24 into 5 into 10 to the power minus 7. That means 120 into 10 to the power minus 7. So x to the power 4 equal to this much. So by putting the fourth root, we get this value of x equal to less than 0.06. Clear? Now come to second bit. And second bit says that the number of term in the approximation to find the result correct up to 10 to the power minus 10. So here we have to find out how many terms are required for this approximation, and the result is 10 to the power minus 10 time 10 to the power minus 10 place of we have to correct. So from this here we have to find the number of term and correct up to 10 to the power minus 10, and this x value lies between 0 to 1. Clear? So let for finding number of term, that means we have to find what is the value of n. So 1 by n 1 by n plus 1 factorial, and here we obtained m4. This m4 value is how much, or the maximum value is how much, 1. So don't worry about this m4, and here we put as 1 and less than, here we truncate this error, that means this one is 5 into 10 to the power we have to 10. Here we take next term, that is 10 to the power minus 11, and solving this we get, or by hit and trial method we can find the value of n equal to greater than equal to 14, or if we take the here 1 by 14 plus 1, that means 15 factorial is always less than equal to 5 into 10 to the power minus 11. Clear? So we get here the value of n equal to 14. So number of terms required is 14 or 14 larger number. Clear? So now come to interpolation. Clear? Here in general, if there are n plus 1th distinct point, that is a less than equal to x naught less than x1 up to xn equal to b, that means our starting point is x naught and ending point is b, and this interval ab is divided into n plus 1 sub parts, then the problem of interpolation is to find out the px and satisfying the condition. First condition is p of xi into f of xi, or second condition is p of xi equal to f of xi and p dash of xi equal to f dash of xi, and these I are run between 0 to n and here also 0 to n. In this case, this first interpolation we get the Lagrange and Newton interpolation formula, and in second we get the higher order. So here we get the Hermite interpolation. Clear? So first of all let us discuss about what is Lagrange interpolation, and here Lagrange linear interpolation. In this case the polynomial px can be approximated as x minus x naught divided by x naught minus x1 into f of x naught plus x minus x naught by x1 minus x naught into f of x1. Here there are x naught x1 are the nodal points. Clear? And the truncation error bound is for this Lagrange linear interpolation polynomial, we get h square by 8 into maximum of this a less than equal to x less than equal to b, and f has the second derivative of x, and this mod is always less than equal to epsilon. For problem point of view, uh, please refer to book. Here we get the function fx, this is equal to sin x. This problem is given. You can refer this book and find out this problem. Clear? Now Lagrange quadratic interpolation. Here quadratic interpolation, that means we have three terms. Clear? So this polynomial is written as p2x, and here we get x0, x1 and x2. That are the three nodal points. So the formula is given as x minus x1 into x minus x2 by x0 minus x1 into x0 minus x2 into f of x0 plus x minus x0 into x minus x2 divided by x1 minus x0 into x1 minus x2 into f of x1 plus x minus x0 into x minus x1 divided by x2 minus x0 into x2 minus x1 into f of x2. Clear? This is the complete formula for finding this p2x. And for higher Lagrange interpolation formula, refer to book. This is only quadratic interpolation formula. Here I provide only quadratic. Clear? Now come to Newton divided difference interpolation. So Newton's divided difference interpolation is written in the form of bracket form. Clear? And the nodal point are written in separated with commas. Clear? Here f of x naught in comma x1 comma x2. There are three nodal points, and the formula for finding this value is equal to f of x1 comma x2 minus f of x naught comma x1 divided by x2 minus x naught. Clear? And by expanding this, we get this denominator as x2 minus x naught. This gives out and 1 by x2 minus x naught, and whole thing is multiplied with, we open this thing, that is f bracket x1 comma x2. This gives f of x2 minus f of x1 divided by x2 minus x1 minus, this one is f of x1 minus f of x0, x1 minus x0 divided by x1 minus x0, and bracket close. Clear? So in this way we can expand this bracketed Newton's divided difference. So this gives our formula for finding the polynomial. Clear? And f of this one is the kth time. This one is f of x naught, f of x naught comma x1 comma x2 up to xk. This gives f of x1 x2 up to xk minus f of x naught x1 up to xk minus 1 divided by xk minus x naught. And here the k value lies between 3, 4, 5, 6 and so on, because here I write x naught x1 x2 and next another term is x3, and similarly 4, 5, 6 and goes down up to n times. Clear? This gives the Lagrange quadratic interpolation formula. So in this video I explain only these things, and stay tuned. If you like my video,